Oh, good morning, everyone. I hope you had some really strong coffee this morning, because I'll be starting today with the internals of React Compiler. Because last year at ReactConf, the meta team introduced React Compiler, which is a build time tool that automatically adds memoization to your components and also enforces the rules of React. But the auto memoization is personally what excites me most, because this means that we finally don't have to manually add use memo, use callback, or react.memo. Instead, we can just write clean and simple React code like this one, and React Compiler automatically transforms it into highly optimized JavaScript code with caching logic that would be pretty much impossible to achieve manually. And the good thing is that we never even have to see or maintain this code. All we have to do is install compiler, configure it with our build pipeline. But what exactly happens behind the scenes to turn our simple React code in this more optimized code? Well, there are many phases that our code goes through in the pipeline. You can also see all these phases in the React Compiler playgrounds, if you've ever worked with that. Way too many to mention in 25 minutes, so in this talk, I just want to go through some of them, the most important ones. But before I get into compiler, I first want to focus on the problem that it's solving, because why do we even need memoization in React? Well, let's take this code, for example. So we have an array with some users. We have a user stats component that filters out the users to find the ones that are active, and it shows the count. And then we also have a main app component that shows the active user count and a way to sort the users in the list. Very clearly, demo code. I know this is not very production, but it gets the job done for today. Now, there is a pretty big performance issue in this code, because our app component is stateful. We have a sort state that we can change from ascending to descending. But whenever we update the state, for example, in user sort, the app component re-renders. And by default, as we know in React, when a component re-renders, so do the child components. So this means that whenever we change sort, user stats also gets re-rendered, and this function component gets re-executed. But within user stats, we're filtering the users array. Now, this is not a big deal if we just had these 3 users, but if we had 10,000 users, this has major performance implications. So before anything can render, it first has to filter through all these users. But the issue is that the users array hasn't even changed. It's just re-rendering because sort changed. So it's completely unnecessary that this re-rendered. So to avoid this re-rendering, we could wrap this component in a react.memo, and this just tells React that we only want to re-render this component if the values of the props have changed, so in this case, the users array. Now, we could also be a bit more specific and say that we only want to avoid the filter function from rerunning on every render, and then just wrap it in a use memo instead. And in that case, we only rerun this filter function whenever users changed. But this approach does have some downsides, because now let's say that we also want to filter the users based on their department. Well, now we cannot forget to also add the department value to this dependency array. If we forget to add this, the value of active users will not update whenever department changes. And this is a mistake that I still make pretty frequently, and this is like the biggest downside to use memo. So this is exactly what React Compiler solves. Instead of having to manually identify these expensive computations, wrap them in a use memo, and having to remember this dependency array, the compiler automatically takes care of memoizing this for you. But how is it able to do this? Well, you already saw all these phases, but I just want to talk about some of the most important ones, starting with the high-level intermediate representation. So the very first thing that the compiler does is transforming the code into what's called a high-level intermediate representation, or HIR for short. And whereas we write our function component as just a single block of code, the compiler needs to see each and every operation separately to really understand what's going on in your code, and also what parts can be optimized. So you can see each of these steps represented as individual instructions with a unique ID, a value where they get stored, and also the actual operation. So when we look at our function component, the compiler sees that we first destructure the user parameter, we then load this user's variable from memory, we access the filter method, create the filter callback function. Then within the callback function, we load the parameter. You get the point. Like, it sees it on a very granular atomic level. So now the compiler has a much clearer picture of every single operation, but especially how the data flows within the code. For example, we can now see that instruction 13 returns variable 19, which contains the JSX created in instruction 12, and this JSX element in turn combines the text from variable 17 and the dynamic count value. So these are all connected. And in the same way, instruction 9 loads the value from variable 14, which in turn uses the value stored at 13 to access the length. So by transforming our JavaScript into this HIR, this high-level intermediate representation, the compiler now has a much clearer picture of every single operation that happens and how the data flows. But there is still one issue with the way it's currently written. Now, you might notice that each variable has a unique identifier. We have users 1, active users 11, count 15, and so on. And this works well in the simple example that I just used, but now if we take a look at a more complex example, let's say that we now are also passing a filters prop that has a limit results property on it, and we then conditionally reassign active users based on whether the user wants to limit the results. Now the HER looks something like this, which is a little bit more intimidating, but all that matters here is that we're sorting the active user or storing the active users variable here. We load the filters prop, we access the limit results property on filters, and now finally we get to the if statement. And this is a conditional. Now on this line, it essentially says that if filters.limitResults is true, then execute block 4, which is the block with the slice method. Otherwise, just go straight to block 3. Now the issue here is that the active user, or is the active users variable. So you can see here that we're using the same active users variable, active users 12, multiple times in this code. But the problem is that the same variable now refers to different values depending on which code path we took. If we came directly from the first block, so when limit results is false, then active users just contains the filtered array. But if we came from the third block, when limit results is true, it now contains the filtered and sliced array. So the compiler now cannot know at build time what the user might select. It could be true, it could be false. So with the current HAR, the compiler cannot safely optimize the value of active users. So this is where the next phase, single static assignment, comes in, or SSA. Single static assignment is a form within the HAR that ensures that each variable is assigned exactly once. So now you can see that each assignment gets a unique variable name. We have active users 42 for the filter method and active users 52 for the slice operation. But notice that both of them lead to the third block, and the third block is where these two code paths kind of come together. So now if we came from the second block, or we have a 5 function here that essentially says if we came from the second block, then use active users 52. But if we came from the third block, so if limit results is true, then use then use 42, which is the filtered and the sliced one. Now, again, in our original code snippet, this was not an issue. We didn't have any variable reassignments that could create this kind of ambiguous variable statement. So in that case, the SSA transformation still happens, but it's more straightforward. Each variable still gets a unique name, but much simpler in this case. I just wanted to show it because throughout the rest of the demo, you'll see the other variable names, so I just wanted to let you know that this happened. So we now have our data flow pretty clearly mapped out, but the compiler still needs to understand 2 critical things: the types of data that we're working with, and also what each operation actually does to that data. So first we have type inference, and this is pretty easy. Here the compiler figures out whether the values are primitives, objects, functions, React elements, and so on. But now it also needs to determine how these operations interact with the data. So now it runs what's called effect analysis, and this examines how each operation interacts with the data. And an effect just describes how an operation interacts with the data, whether it reads it, changes it, modifies it, and so on. And this is really important later on for memoization because the compiler needs to know which operations are safe to cache and which could break if they were cached incorrectly. So there are 6 types of effects. So in our case, we first have some read effects, like accessing a method like filter or length. So a read effect doesn't change anything about the code. So any read effect is perfectly safe for caching. We also have some store effects, and these are store effects where we assign new values. So these are safe to cache as long as the value that's being stored does not depend on any mutable data. Now we also have capture events, and these are events for loading values from outer scope, so function parameters or previously stored variables. And these create dependencies that the compiler needs to track to have the correct memoization. We also have mutate effects. These are operations that might modify depending on what happens at runtime, and that's the majority of it. Lastly, we also have freeze effects, and these make values immutable, so they guarantee that they cannot be modified later. And the compiler just adds these to make sure that the data won't change, making them safe to cache. Okay, so finally at this point, the compiler now understands what each operation does and how it affects the data, but it still doesn't know which values change between renders. So for example, we know that instruction 3 has a read effect when accessing filter, but that doesn't tell us if the user's array can change between renders. Maybe it's always the same static array, maybe it comes from props or state, and so on. So the effects analysis tells us the potential for change, but it doesn't tell us whether it'll actually change, or the change that actually matters in React, if it can change between re-renders. So now it's time for the next phase, reactive analysis. So during this phase, the compiler has to figure out which specific values in these components are reactive, meaning that they can change between renders. So just to make the code a bit more readable, I'll just remove the types, because otherwise I have to make the font really small, but they're still there. So the compiler first starts by looking at the source of each value. And to check whether it's reactive, it begins with the values that are definitely reactive, which are the function parameters are always reactive because they come from props that can always change between renders, and also hook calls produce reactive values like use state, use context. But in this case, we only have function parameters. So now the function parameter is marked as reactive, but it then traces forward through the data flow with a simple rule. If a reactive value flows into an operation, this output becomes reactive too. And what this means is, looking at our example, the user's parameter starts as reactive because it's a function parameter, but we now have a reactive value. 23 becomes reactive as well. And then we load users on line 2, so 24 becomes reactive as well. Then we access the filter property on 24, so this also gets reactive because we loaded like the reactive user prop, so 25 also becomes reactive, and so on. So anytime there's any reactive input, the output becomes reactive as well. So just to zoom out a little bit, what are we really looking at here? Well, really what we're saying here is that for the initial prop destructuring, we create a new binding, but this is of course reactive. This prop can change between renders, and that's what this current HER is saying. Then we load users 22 into this new temporary variable 24. This is also reactive because we're reading the reactive users 22 variable. So the value of this specific atomic thing in our function can change between renders. Now, accessing the filter method here can also change between renders, because if we're working with a brand new users array, and arrays are objects, meaning an entirely new object, this filter method would be on a brand new object. So this can also change between renders. So again, this phase ensures that every value that could change between renders gets marked as reactive. And these reactive values are exactly what the compiler wants to optimize. There's no point in memoizing something that never changes, but values that can change between renders are perfect for caching. So now the compiler knows both the behavior of the operations from the effects and also which values actually matter for reactive rendering for reactive analysis. Okay, so at this point, we've got our code broken down into an HER, tag with types, effects, reactive annotations, and so on. And we also know what values can change between renders. But now the compiler has to decide which operations should be cached together and which ones should just run every time. Variables that change together must also be cached together. So now it's time for the next phase, which is scope discovery. So now the compiler has to decide, okay, which operation should be cached together. But the idea is that variables, again, like I said, that change together must be cached together, and variables that change independently should be cached independently. So during this phase, the compiler groups the operation based on their dependencies. So operations that depend on the same inputs get grouped into the same scope. So after scope discovery, our HER now looks something like this, where we have 3 scopes. First, we have scope 0, which is just the callback functions, because functions get their own scope, because they can just be memoized independently, because it doesn't depend on any reactive values. So this can be cached once and then reused across all renders, pretty much. Now, scope 1 covers instructions 3, 5, and 6, and these all depend on the user input for this filtering operations. They all need to recalculate whenever the user's array changes, so these all get grouped. So zooming out, this entire filtering operation now becomes its own memoizable scope. This is almost like we just had with useMemo, but now it's done automatically by compiler. And the filter's callback also gets extracted entirely, because this doesn't depend on anything, and this could just be reused across all renders. And we even get a separate scope for JSX creation. So this only recalculates whenever count changes. So if the user's array changes, but the total amount of users is the same, then we can just reuse this cached JSX. And this is something that's pretty much impossible to do with useMemo, but it's done automatically with compiler. After getting, thank you, after getting its own scope, let me get through this, okay? I have 200 slides, all right. After getting its own scope, the callback function now becomes a separate function. So the logic is still the exact same, but it's just its own block. And this is great because we don't have to create a new function object now on every render. So the compiler automatically identifies these like pure functions and extract them, which is much better for performance, which we'll see in the end result as well. So at this point, the scopes just kind of exist as annotations in our HAR, but they need to become actual control flow sources for the code generation. So the compiler now structures the scope into a different presentation that clearly shows which instructions belong to each scope and also what their dependencies and outputs are. So now you can clearly see that scope 1 depends on users or the users variable and produces the filter result, while scope 2 depends on count and produces this JSX. So this explicit control flow is now very important for the next phase. Finally, we get to code generation. So this converts our HAR into the optimized JavaScript that we saw from the beginning. So to do this, the compiler first walks through each scope and sets up cache slots. So we need two types of slots here, one slot for each dependency so we can detect the changes, and also a slot for each output value so we can actually cache the result. So in total, we get 4 slots now because we have dependency users with the output, and then we also have the dependencies count with the output JSX. Now this automatically generates a useMemo cache call, but usually in your React compiler code, you'll just see this as a lower, whatever that's called, low-c, because that's just shorter for the bundling purposes, I guess. So then afterwards, it generates the rest of the code, which now includes our destructured users parameter. We then have our first scope, and we can see here that it first checks if the users have changed since the last time by comparing it to what's stored in our cache slot 0. If yes, then of course run this expensive filter operation and store both the new user's reference and the result T1 in the cache, and if not, just use the previous result from cache slot 1. We then have these unscoped values that just run every time, like assigning the filter result to active users and calculating the counts. And finally, we also have the second cache block for the JSX creation. If the value of count is different from last time, it creates a new JSX and updates the cache, and otherwise just reuse this cache JSX. Eventually, we return T2, and that is the JSX with the count variable. But the nice part here is that all these scopes work independently. So if the user's array has changed, the first scope recalculates. But if the length of the total amount of users hasn't changed, then there's no need to generate new JSX. We can just get the stored one. And getting this specific with useMemo would mean that we'd have to create tiny wrapper pieces everywhere in our code. And you could technically do it, but it would just be a maintenance nightmare. But the compiler does this all automatically. So finally, we've just completed all phases, from HAR, SSA, type inference, effect analysis, scope discovery, to code generation. Now, it's important to understand that React compiler is not a silver bullet. Compiler cannot optimize code that breaks the rules of React, like conditionally calling hooks, components with side effects that cannot be safely cached, legacy stuff like class components, and some more complex JavaScript patterns that the compiler just cannot figure out safely. But the compiler will always try to not memoize anything if it's not sure. Better safe than sorry. Now, if your app is already well optimized with a lot of manual memoizations, you also shouldn't expect like a big performance improvement, because the real win here is the automatic correct optimizations without the maintenance burden. It doesn't necessarily mean that it's always better performance than manually using useMemo. Now, if you're interested in checking out how ready your existing code base is for React Compiler, you can just run this command, npx React Compiler health check, which analyzes your project and identifies components that break the rules of React, or it shows you potential compatibility issues. Now, as of today, the compiler has moved to the release candidate and is preparing for its stable release. But you can already try today in frameworks like Expo or Next.js by just installing the Babel plugin and adding it to your app.json, nextconfig, and so on. If you've enabled it in your app, you can see it working in React DevTools with all these like little sparkly memos. These are automatically memoized by React Compiler. So finally, I'm done. So with React Compiler, we no longer have to choose between writing clean code and also having performant code. So the compiler automatically handles all of this memoization for us. And this is pretty much the future of React. It's just performance by default, but without the complexity. And this is exactly what compiler enables. Thank you so much.